Hi, Zoe. Thanks a lot for the kind introduction. So good morning, everyone, as well. So today I'm going to briefly talking about our research study related to the neural architecture search, in particular for the AI systems. I will start with an introduction to the neural architecture search. We also call it as a NAS, and then elaborate on the topology-aware NAS for exploring novel blocks for deep neural networks like DNNs. So here, two methods will be introduced. We call it as a SwiftNet. It's used in graph propagation as a meta-knowledge to search representative neural architecture. And then another one is called auto-shrink. The objective of this project is to discover efficient neural architecture. I will also talk about our graph embedding methodologies. It's used in graph embedding for feature representation. And the goal over here is to improve the search performance and efficiency. And at the end, I will introduce a bit about the computations our team attended before, also the roadmap and the future works along this research direction. So let me start with the neural architecture search work over here. So this page shows and compares the neural architecture search and from the traditional DNN model designs. Basically, NAS is a subfield of what we call auto machine learning or auto ML. It is a common approach in designing state-of-art DNN architectures in order to address the needs of various AI applications. So basically, when we're talking about the traditional DNN architecture designs, they tend to manually tune the network structures and then empirically find the best solution that can meet the target dataset's requirement. So NAS adopts an automatic process to explore the DNN architecture. And of course, we have to design space and select the best solutions and based on the feedback matrices and retrieved from the target data set. So in fact, there have been a lot of NAS works and many of them focusing on discovering high performance models for challenging tasks. For example, we're talking about the image recognition, object detection, and so on and so forth, right? And recently, some other research studies and start concentrate on efficient DNN architecture, different platforms and tasks. Both directions are very promising and gain a lot of attention recently. So on this page, I actually show the latest result from NAS methodologies. And as you can see, NAS method have achieved much better DNN architectures than those found by traditional manual approach. For example, left figure over here present the performance of the DNNs on ImageNet dataset. The efficient net family, which is represent the NAS approach, obtains much better Pareto frontier than state-of-the-art handcrafted models. For example, inception models, ResNets, and DenseNet. So the right-hand side is the Penn Tree Bank language tasks. DARTS model in orange over here, it actually achieves some lower perplexity compared to traditional hand-designed OSTMs. Right. So generally speaking, the NAS development can facilitate the DNN architecture exploration for different AI tasks on various hardware system. And this is essentially, our goal. So let me move to some introductions on the NAS approach. Basically, there are three key components in NAS. We call this as a search space, search strategy, and the performance evaluation strategy. So search space and basically decides the types of the architecture that we may explore in general. For example, very popular approach is using mobile net V2 blocks to construct the search space. So in this way, we may explore only those architectures and similar to mobile net V2. And the search strategy determines the way of exploring the search space. So the simplest form is random sampling. Basically, it's randomly samples and candidate from the search space at a time, and eventually we can pick the best candidates as the final model. Right. So interestingly, we find not only us, but many researchers and find like a model crafted by random sampling can achieve a much better performance than those crafted by human expert. And therefore, the random sampling usually is adopted as the baseline to compare different NAS methodologies. Okay. How about this performance evaluation? So performance evaluation strategy reflects how to evaluate the architectures and retrieve their performance on the target data set. So a common approach here is to use smaller portion of the data in the target data set as in proxy. So here the assumption is that the evaluating candidate architecture under the proxy setting will result in similar ranking correlations as we evaluate them on the full target data set. So the major challenge over here in NAS is evaluating the full target data set usually is very time consuming and also resource consuming. Therefore, the proxy-based performance evaluation is commonly adopted to address the search cost challenges. So here, I actually present the search space overviews. Main reason is the search space is very critical to the NAS algorithm development. As it decides the potential operations that'll be the best architecture may generally have, right? So the search space can be constructed in two ways. Generally speaking, we see cell-based search space or node-based search space. So cell-based search space tend to utilize existing architecture motif as backbone cell structure and then use it to build the new model. For example, I mentioned about the mobile net V2 blocks. Okay, the NAS search for the best combination of those blocks, will construct for optimal DNN architectures. And then with the different hyperparameter settings in the, for example, mobile net V2 blocks. Okay, node-based search space tends to treat the NAS problem as finding the best building blocks for DNN architecture. So this research line tends to search the best inner cell structure using graph-based search space, and then aims to explore novel cell structure that have not been discovered before. In fact, we can also leverage this in two approach together and obtain we call the hybrid search space to simultaneously explore novel cell structures and the best combination. And of course, this is going to increase the design complexity. And on this page, I give a brief comparison of the two types of the search spaces. And as you can see, cell-based search space use predefined architecture motifs, and they may save block designs and provide good intuition for constructing suitable DNN architectures. Also, cell-based search methods are easy to implement. For example, representing the search space with the mobile net V2 block, it's very neat and simple. We only need to record a few hyperparameters to represent each block. The problem of a cell-based search space is it's usually suffer from anonymous search cost because it has to associate with the topology agnostic approach. And for this line of research, and we usually need to draw many samples from the search space before we are able to find qualified architecture. And also architecture obtained by cell-based method are quite similar to each other. So it's not easy to find an intuition what kind of the architecture works the best in the search space. Node-based approach usually spend more efforts on finding new block designs for DNNs. So typically they use a fixed depth or width settings when searching for the optimal building blocks, and then apply in different depth and width settings to get a final architecture. So these architectures and likely suffer from we call suboptimal performance, mainly because the search space usually is not large enough, and also construct a node-based approach like encodings and implementations is a lot of complicated. So never mind. I guess the architecture engineering process and yearly is very time consuming for sure. Recently, node-based works have reduced the search cost from thousands of GPU hours to only 10 GPU hours. Our recent work, Tsing mentioned, Outshrink further reduced this to a few GPU hours. And in this approach, we incorporate topological information during the search process. So generally speaking, the extensive search cost is induced by one, the large space, and two, the redundant evaluation of correlated architecture in the search space. So the computation time for correlated architectures in the search space can be reduced by incorporating topological information. And then we are able to prune out and important search spaces and during the process. And this is, in fact, aligned with the goal of our, what we call topology awareness, to accumulate graph level topological knowledge in the search space, and then eventually speed up the search process. So this is a kind of a general introduction of the basics of NAS. So in the following, I will extend my talk to our topology aware NAS methodologies. More specifically, here I will present two approaches that follow this methodology. We name it as in SwiftNet and AutoShrink. The first one uses graph propagation as a mental knowledge for search, and the second one tends to discover efficient neural architectures. So I will quickly go over those technologies, but I also post the link or the information of our publications, and so you may refer that and let me know if any question. Okay, so I will start with the topology awareness over here. Again, as I mentioned, our goal is to address the high search cost issue. From the methodology perspective, we tend to incorporate topological information into the search space. So have the same intuition as the node-based NAS. Our methods tend to find the novel blocks to construct the final DNN architecture instead of utilizing existing architecture motifs. So as we show in the figures, the topology awareness treats in DNN architecture as the stacking of the cells, and each cell is composed of the combination of the operations. So here, for example, we take ResNet 20 as an example. It's composed of an ResNet blocks, and each ResNet blocks could contain, for example, 2 3x3 convolutions, and then each 3x3 convolution denotes as in one node operation. Okay, so well, cell-based NAS mostly focusing on vision-related tasks, and the node-based NAS, and therefore we call the topology-aware search can be applied to both vision tasks and also the language tasks. So one of the most important features of topology awareness is that the directly acyclic graph and DAC are used as a prototype to construct a search space. Basically, each node in the DAC represent a DNN operation. So in CNN, for instance, as we illustrate over here, for example, a convolutional layer can be taken as an operation, and we use the future concatenation to aggregate inputs. Well, for the RN designs, the basic operation could be an recurrent fully connect layer with an, for example, a carefully designed activation function over here, and then the weighted addition is used to aggregate inputs. Okay. So on this page, in fact, we illustrate the entire flow of the SwiftNet. It is an SwiftNet is an application for our search space in vision task only. So it removes the concept of the width and depth scalings and only uses DAC to represent the whole search space. So more specifically, here we introduce and we call the mentor graph, which is composed by several DACs. And then multiple DACs are adapted within the same stage of the network. And then we do downsampling to connect the different DACs and from different stage. Okay, so with this mentor graph semantics, and SwiftNet has a much better Pareto frontier than most of the handcrafted architecture and also AutoML models. So as I showed over here, this was kind of a results more than a year ago. So what we do essentially is composed of 3 stages during this designs. So A, we actually have a multiple subgraph of the DACs, and we use them to provide a candidate architecture within the search space. So each DAC over here is sampled independently, and therefore the candidate architecture sampled from an extremely large design space. So afterwards, okay, we use the matrix retrieved on the proxy data set as an evaluation for each of the candidate architecture. Okay, so this is kind of a common approach. And finally, the mentor graph accumulate knowledge by following this update process. So here we use an W to denote edge connections in the mentor graph, and use an alpha, beta, and eta as in hyperparameters to control the mentor graph learning processes. So as you can see here, we tend to learn this in mentor graph, okay? And therefore this in stages, it conclude workflow of the SwiftNet, okay? So on this page, and I wanted to show the architectures and we discovered. And as you can see, the SwiftNet architecture is very different from like a common, widely used neural networks. Basically, SwiftNet architectures and have more complicated inner connections, as you can see it over here, and others are mainly composed of repeated blocks. SwiftNet also present a completely new design philosophy, like it does not utilize any inverted bottleneck structure over here. So our design, we were joking like this is fat, but shorter, okay? So SwiftNet mentor graph and can serve as an intuition for designing novel architecture. And during the explorations, we observed that not all the part in the SwiftNet mentor graph contribute to the improvement in the performance matrix. So this observation actually holds when it comes to a full search space represented by completed DACs. And therefore, we propose efficient NAS methodology and call auto shrink over here. So methodology-wise, we tend to progressively shrink search space and remove redundant edges to optimize the cell structure. So for a given cell topology, auto shrink kind of inherited topological knowledge from the previous architecture and then craft and topology shrink space. So as you can see it over here, for instance, in K candidate selection strategy is adopted. So it selects only K cell topologies and from the topology shrink space. And finally, we evaluate this in K cells on the process data set and use the best one to update the cell topology. So we will stop when the search matrix and stop improving in this way, a much simpler, but quite good performance in cell topology can be derived through the process. I like to elaborate a little bit further on the topology shrink space over here. So for a given cell structure, for instance, a topology shrink space is crafted by applying we call graph damage to each net, each edge basically, and then we collect the derived structures. So if we have M edges in the cell topology, and then the topology shrink space will give us an M different cell topologies, right? And then consequently, the K candidate selection will randomly select and K candidates and from this and shrink the space for the final evaluation. And the different from a performance-driven method like a DARTS, auto-shrink use a resource-aware search objective to trade off performance and resource consumption. So the search matrix could be penalized by a soft resource constraint parameter lambda over here. And for example, for CNN architectures, and we use a MAC multiply accumulation numbers to penalize an extremely large models. And for the RN models, and in fact, we use parameter numbers. And here, for example, lambda equals to 0.01. So 10% of the accuracy is penalized by 1 magnitude parameter counts. Okay, so we could, this is a hyperparameter, and we could change during the training. So let me show the results quickly. Basically, the cell explored by the auto-shrink methodologies are quite representative and novel. Well, state-of-art auto machine learning models and takes thousands of the GPU hours to explore. For our cases, as you can see, we can find this in cell structures within only like 1.5 GPU hours. And also the DNA architectures and craft by using our cell topologies can achieve comparable performance as other methodologies. Okay. Well, next, I will also quickly go over we call graph embedding method. The method can provide a more robust feature for representing the DAG-based search space. So this is kind of the continuity of the previous work. So when we're talking about the gradient-based networks, usually we extract a adjacency matrix as the feature vector for DAGs. So what we observe at it's not easy to use adjacency matrix of two different graphs and define their similarity. So that means like adjacency matrix do not present intergraph information while being used as a features. So gradient-based methodologies and usually have to map architectures to their predicted performance within a discrete topological space. And as you can see, this causes inaccuracy, this causes reduced representation capabilities, and so on so forth. So NAS-GEM methodologies, and we propose and intend to address this issue. So we adopt an graph similarity measurement SE over here, and it can quantitatively measure the similarity between two different graphs. So visually, as you can see, these two graphs shows a higher similarity. These two have a higher similarity, but these two and the similarity is much lower, right? So the derived graph vectors and contains kind of a more abundant information than plain one hot graph vector, and therefore we can use it as a better feature vector for gradient-based and nested search. Okay, and this page I'm kind of giving the workflows. We use graph embedding to represent the graphs in a continuous space, as I mentioned on the previous page. And then we adopt an encoder to train the graph embedding. And then during the search, we introduce an efficient score predictor. And then we use this predictor to estimate the performance instead of trying to optimize the architecture weights. And therefore, at the end, we use the trained predictor to explore the best architecture in the design space. So this is kind of a very conceptual, and this paper recently accepted by AAAI next year as well. And this is a link to our online version. So I will just quickly go through the results on this page, and we give them visualization and show the graph embedding methodology. So the left one then shows like with graph embeddings, it can result much smoother surface of the efficiency score predictor compared to the counterparts without graph embedding. And obviously a smoother surface indicate that it is easier to find the best architecture in the design space, okay? And here is the result. And finally, as you can see, we can use the best architecture we find and evaluate on the image data set. It obtains a much better performance than other gradient-based method and have a very similar low search cost as a gradient-based method. Okay, the figure on the right-hand side then shows our method can also achieve a better efficiency score than random graph price in only 0.15 GPU days. It's basically 500 iterations. Okay. So the most important information we wanted to convey with this methodology is it is very helpful in boosting the performance of the existing gradient-based NAS method. I really like to talk to students, and in fact, our students attend some competitions related to NAS. For example, last year, our NAS model achieved the highest accuracy on Visual Wake Word Challenge. And our students also attend the on-site low-power image recognition challenge on ICCV 2019, and the team won the second place with the we call the DukeNet models. So what we do on this, and basically we redesigned the mobile net V3 architecture in order to make it fit better into the hardware platform given by the computation. It is in Qualcomm Hexon DSP. So for example, large kernels, fancy activations not favorable and cannot be well supported by the Qualcomm Hexon DSPs, and then we have to reduce the kernel size and we have to remove those fancy activations. And fully connect layers and consume too much memory operations, and then we actually remove many fully connect layers and invest more computation budget on convolutional layers. We increase the number of the filters, and we also increase the width multipliers to fully utilize the 7 millisecond budget given by the organizer. Actually, if you go to the online, so we have the entire set of the our code and published on GitHub as well. So at the last, I would like to talk a little bit more about our future research work on this research lines and also the roadmap of our lab. So we believe the reproducible architecture search process is very, very important. Basically, how can we use the same benchmark? Are we able to provide more details on hyperparameter tunings? How to regulate the random seeds, indeterministic CUDA-CNN settings, and so on and so forth, and to ensure reproducibility and also ensure the fair comparison across different methodologies. We also extended NAS to broader domains like detection, pose estimation, question answering, so on and so forth. And there have been some works in our groups on this line. Finally, let me present the research roadmaps in our lab. I know many of the students and kind of have a very strong, in Taiwan, have a very strong circuit and architecture background. Our team, in fact, has been extensively working on the circuit and architectures related to the AI applications and the hardwares. So we do ASIC designs, FPGA-based designs and optimizations and for GPU and CPUs. We also conduct a lot of compression and acceleration work on the AI and DNN models. One of the representative work on structure sparsity already gained more than 1,000 citations within like 4 years also, I guess. In fact, we have been serious and work and collaborate with the industry companies. So today I'm mainly focused on the NAS, right? This is our latest research studies and industry companies like Facebook, Qualcomm's and kind of devote quite efforts and together with our students. We also work with distributed machine learnings and machine learning security topics and so on and so forth that I haven't got a chance to include it over here. So, but I hope in this kind of give you in general overview of the research in our lab. And in case you have any further questions, then feel free to send me an email and we can talk more about this. So this is basically what I have and regarding about our research on NAS.